Question 10, we've reached the end. How very exciting. We've got two ice skaters in a performance and we're going to figure out the mass of the woman. So we're going to use our momentum equation for this. We know that momentum P is equal to mass M times velocity V. Now they're both moving as one, so it's going to be the total mass times the velocity of the whole man-woman combo will give you the momentum of the whole thing. Let's see, we've got momentum, total momentum is 371. It's kilogram meters per second, which is the proper units. We don't need to do any converting there. That's going to be equal to the total mass of the man-woman combo. We know that the man's got a mass of 64.5 kilograms. What we don't know is the mass of the woman. But we know that we've got to add it to the mass of the man. You could call it M with a little W there, because I've already used M there. It doesn't really matter. You could use D, or your favourite letter of the alphabet, whatever it might be. You need to multiply by the velocity. The velocity is 3.50, as you can see. So that's the mass, that's the velocity, that's the momentum. We now need to rearrange to get MW as our answer. Incidentally, do be careful with this mass thing. The proper units of mass is kilograms, which is weird, because usually when you see kilo you're thinking, that's not good, we need to convert that into not kilo. Don't convert it into grams to use the equations. Mass is the only thing that you leave in kilograms. Kilograms is the official unit for the equations. If you get an answer or some data in grams, you need to convert it into kilograms, the official unit. The reason why it's that weird way is to do with the French Revolution. Not really enough time to explain it in this video, just take it from me. Leave things in kilograms for your equations. So we've got to find the mass of the woman. Well, at the moment, it's got all this gubbins in it. We want to sort of take it stage by stage. I can't get rid of this yet because this is still being multiplied by this. I can divide both sides of the equation by 3.5, and that will just leave me with this bracket on this side. So I end up with 371 over 3.50, let's just call it 3.5, is equal to 64.5 plus the mass of the woman. Again, I'm going to call it M with a little W. It doesn't really matter what symbol you use. So clearly if we do 371 over 3.5 and take away from that 64.5, that will give us our mass. So 371 over 3.5 minus 64.5, because we've just taken 64.5 off both sides, is equal to the mass of the woman. If you run those numbers, you'll find it's 41.5 kilograms. 41.5 kilograms is the mass of the woman. There we go. That's a full marker. So you got 1 mark for putting the evaluation in. So this is your first mark here. Rearranging it, there's your second mark for that one there. And then for your third mark, we had the evaluation, and the mark that I've just missed is putting the numbers in the first place. That wasn't quite as clear as it could have been. There is the mark scheme there, your 4 marks there. If you got the right answer without working, you got all 4 marks. But you're playing a dangerous game, because if you've got any of the calculations wrong at any stage, you would lose all 4 of your marks if you just put an answer and it was wrong. So do make sure that you include your working every single time. Right, our second part, our last calculation of the paper, is the kinetic energy of the man. So if we're calculating kinetic energy, unsurprisingly we're going to need the kinetic energy equation. Kinetic energy is a half mv squared. There we go. So let's get that equation in. Kinetic energy is equal to half mv squared. Do be careful with that squared, a lot of people forgot to put the squared in. So we're going to need the mass. So it's going to be half times the mass, which is, is the kinetic energy of the man. So we're going to have to be a bit careful here. We're going to have to use the mass of the man, not the mass of both of them together, or the mass of the woman. Man's mass is 64.5. 64.5. And then we need to multiply by the square of the velocity, which we're already told is 3.50. Square that. And then, again, shove it in a calculator and it will just tell you directly what it is. 395 joules. There it is. Not much more to than that really. One for substitution, one for evaluation. So one for getting the numbers in and 1 mark for finding out that it was 395 joules. They would allow you answers that rounded to that. So if you put 395.0625 for example, which they've actually quoted on the mark scheme, they would give you the mark for that. But that potentially is generous. We shouldn't be giving answers to loads and loads of significant figures, particularly if you're sort of including loads of decimal places in there. It's not really the thing. Okay, our final question of all the questions on the paper. Question 10b. Okay, so we've got our man, we've got our woman. The man's staying in the same place on the ice throughout the sequence, and the woman is being spun around. So she starts off here. She's moving at a constant speed at the start of the sequence. The man's holding her arm, so of course she's going to go round the man. She's going to go round the man several times, and then he's going to let go of her arm, and it doesn't tell you what happens then, but you can figure it out. You're going to explain the motion of the woman, and to be clear, it says in terms of the forces acting and the effect on her motion for the whole sequence. So those are little things that you want to make sure that you're hitting in the answer. Sometimes the 6 mark question can be a bit daunting, can't it, because you're thinking what is it that they're looking for, but they will usually list things like that. You can think, oh well, maybe I'll make sure that I've got a few sentences for this, a few sentences for this, a few sentences for that, and that should cover me. So again, best bet with this is to look at the mark scheme, to draw out the answer from that, and to draw your attention to what we're looking for. So, slightly different to the 6 marker earlier, in that the descriptors are a little bit more specific, perhaps. So for the level 3 5 to 6 marker, to get this at the high marks on this, we had to have accurate and relevant physics understanding throughout, so getting the physics right, understanding of the scientific ideas being detailed, fully developed. The explanation is supported throughout by linkage and application of knowledge and understanding of scientific ideas. So it's not just about throwing different ideas down on the exam paper, it's about linking them together in order to get those high marks. So that's what we're aiming for. So what could we say? Again, you don't need to put all of these things in your answer in order to get full marks. This is a general description of the answer in its fullest form, but you wouldn't need all of these things to get into the top marks on the mark scheme. So let's see. You need a force to keep an object moving in a circle. We know that from Newton's laws, specifically Newton's first law. An object will just keep on going in a straight line at a constant speed unless acted on by an overall resultant force. So if we're going around in a circle, there must be an overall force acting. So we're looking at this from the top. Here's our man, here's our woman. Not the most complicated of diagrams I've ever drawn. And he's holding on to her. There must be some sort of force that stops this woman just from flying off in a straight line, because that's what things tend to do if there's no overall force acting on them. So there's this force, this centripetal force, which is pulling her in. And in this case it's coming from the fact that the man is grabbing her. We've got a sort of tension in the arm as he pulls her in towards the centre. She's moving in this direction. So that's her velocity at the moment, her instantaneous velocity. She's moving this direction, she's been pulled in this direction. The result is that she'll change direction. She'll keep on going like that. So maybe, a quarter of a cycle later, she'll be in this position, and again the man will be pulling her in, and she'll be moving in this position, and so on and so forth. Good. Now, so we have this idea that the force is needed to keep an object moving in a circle, otherwise we wouldn't be changing direction. When moving in a circle, the direction of the velocity is changing. Okay, we're curving around, we're changing the direction that we're facing. There must be an acceleration. If you've got a change in velocity, you've got an acceleration. Remember the equation, A is v minus u over t. If we've got a change in velocity, So v minus u is some number. V is not the same as u. The velocity is changing. We must have an acceleration. Okay, even if the speed is the same. Now, having thought about that for a second, this is not a particularly great way of phrasing it, because if she's moving at a constant speed, technically, if you put the speeds in, it will look like you've got no acceleration there. What's actually happening, of course, is that the speed is constant, so she's maybe moving at 3 meters per second the whole time, but her velocity is still not constant because she's keeping on changing direction. So perhaps we shouldn't be thinking about that after all, but that's okay. If you're answering a question like this and an idea comes up, and then you're looking at it later on, you realise that it's wrong or it's irrelevant, you can reject it out of hand. The idea, of course, is when you come to a question like this, you think it through first, you figure out what you're going to say, and then you commit your ideas to paper. There we are. That is why I deliberately brought that equation in when it wasn't as relevant as it could have been. He lied. So we've got a change in direction. We must have an acceleration because our velocity is changing, therefore we're accelerating. Moving in a straight line with no resultant force at constant velocity. So this is when they let go. So when the guy lets go, the woman is just going to keep on going in a straight line. So she's going round and round and round, and as soon as he lets go, there's no force there, no tension, no centripetal force. You just keep on going in a tangent. If she was released here, and she comes round, she'd go off in this direction. If she was released here, she'd go off in this direction. So she'd move in a tangent to the circular path. Good. The woman's changing direction while circling the man, we've covered that. She's changing her velocity but not changing speed, therefore she's accelerating. This requires a force towards the centre of her orbit, which is a centripetal force. A centripetal force means the force is acting towards the centre. It's a centre-seeking force. Anything going round in a circle must have a centripetal force. Okay, if you're running in a circle, it's friction between your feet and the ground which is pushing you in towards the centre. You'll notice that because if you try and run in a tight circle on ice, it will not go well for you. The planets, as they go around the sun, have gravity pulling them in, etc., etc. So you need a centripetal force pulling us inwards to keep something going around in a circle. When the man releases the woman, the centripetal force ceases. There's no resultant force on the woman. We can ignore the friction from the ice. She therefore continues moving in a straight line, and now she's moving at constant velocity because she's not slowing down. If we ignore air resistance and friction and things, she keeps on going straight speed, good grief, straight line, constant speed, therefore her velocity is constant. Now that's a lot of ideas. That's a longer bullet point list than the 6 marker before, but again, you don't need to cover all of these things. You're just looking to give a solid answer that covers all of the relevant ideas in the question, and again looking at it in terms of the forces acting, centripetal force, tension in the arm, all that sort of stuff, the effects on her motion. She keeps on going around in a circle until that force is removed, and then she goes in a straight line at a constant speed for the whole sequence. Again, sometimes people were talking about just the first bit and they forgot to mention when he lets go of the arm. There you are, that is question 10 done. Well done, you have now finished the entire paper.